Okay, we are officially recording here. So um, I have finally worked the homework, at least the first time. Do not necessarily assume that I have the correct answers yet, because I make just as many mistakes as anybody else. But I thought since I think most of you have submitted this by now, I thought I would just throw my solution up here. You can look, ask questions if you want to, and I'll try to look at that stuff this weekend and get you some sort of a response back. But anyway, so first problem, this is, I think I'm just parroting back, hopefully correctly, the information that was given on the homework. So, we had 9,000 kW on the on-peak and off-peak contract demands. The on-peak monthly real kW was 8336, and the off-peak was 8292. So they're not doing a good job of trying to move KW to the off-peak period. So who knows, that right there, that could be an opportunity. Maybe they never thought about it, I don't know. On-peak energy, 34,853. Of course, that's 6 hours a day, so you expect it to be much smaller. And then off-peak monthly energy, 3,879,361 kilowatt hours. The recorded reactive demand is 2,770, and that's lagging, so that's going to go with the peak, which is going to be this guy right here, I think. And then the leading, which would be at some minimum point. I don't know, did they even give you the minimum? I'll tell you, I can't hardly read this thing. It's not very good. I don't think they gave you the minimum. So anyway. Okay, so into the rate structure. We had a customer charge of 2,000, administrative charge of 350. So their fixed kind of fees on my subtotal is 2,350. Let's go on down here a little bit. Come back up. Okay, so on peak, I don't know if everybody noticed, but this was May, and May's a transition month. So don't be using those summer rates in May. I haven't looked at all the homeworks, but I guarantee you somebody used the wrong rates because you didn't notice that little May 2020 up there, which is not a big deal. I mean, I don't care much, but it was May, a little small, a little hard to read, but so it's the transition month rates are the official ones for this particular month. So your on peak is 927, and that's, times your on peak demand, which was right up here on peak. So I guess that's 8336 times 927 should be 77,000 some odd dollars. And then your maximum, you pick the bigger of these two. So again, the on peak is bigger, so they're going to pay that. So it's $2.43 additional times that same value. So if you add those two together, their demand charge is cool. They slipped it under $100,000. A cool 97,000 and change. Okay. Then the energy charge for the on peak, which, that's this number right here, the 834,000 times the on peak rate, 5.158 cents, $43,061, $62, something like that. And then for the first block of the off peak, you take your 200 hours times your on peak demand. So let's see, F26 is the 200, I7. So let's see if I got that right. I7, that's the on peak demand. So that's correct. Times the ratio what is it? It's the off-peak energy to the total energy. So the off-peak energy is this guy right here, and then the sum of those is the total energy. So that's what we're doing, I10 divided by I10 plus I9. So all that together gets me a first block size, and the second block is the same arithmetic. Okay, so that's what, 1,371,951, and then times the first block rate. There's another $70,000. And then the second block, you just got to make sure that you haven't, you know, you're not paying for more than you use. So, you know, you can just highlight these two cells, and it'll tell you the sum is 2.7 million, but the off-peak energy is 3.8 million. So you've saturated both blocks. So it's the same number of kilowatt hours times this second block rate, which is a whole lot lower. They're getting cheaper. So that's $25,778, $79. And then you take these two, because the multiplier on this block is 400. So it's going to be the sum of these two. Well, you didn't use that many. So for this number, I just took what they used and subtract off these two blocks, or one of them twice. So that says you got 1,135,459 left to pay for, and they're 1.6 cents each. So that's another 18,000. Okay. So I think all this is correct. So I got about 158,000 for the energy. So we've got demand, energy, and fixed charges at this point. Yes, sir. You use the larger. Did I use the wrong one? Oh, excuse me. Oh, I'm not going to take this. These people are crazy. Oh, man. Okay, so you're saying I used 82? Well, crap, that's no good. See, I told you I wouldn't guarantee you this was right. So the maximum times I8, yep. Okay, thank you. See, that's one reason I like to do this, because y'all find all my mistakes. So, because the worst thing to do is to go grade all the homeworks with the wrong key. And then you really feel like an idiot. Okay, is that better? You got me? Thank you. I got my auto save on, so I should be good. Good. Oh, you know, I don't expect you to be perfect, because I'm not perfect. Okay. So hopefully we're using the right numbers here. Okay. So then we get down to the reactive charge. Of course, on the lagging, we take 33% of the maximum meter demand. Did I get that one right? No, I got that one wrong too. Dadgummit. This is an old spreadsheet, and the last time I gave this problem, it was the off-peak was the bigger. Okay, there we go. I think that's right. So you take the bigger of the two demands, off-peak, on-peak, multiply it times 0.33, and this is what's allowable for a 95% power factor, okay? And so then you subtract that from the actual, and the actual was 2,770 up here. So we're pretty close. And on the sheet, the power factor is 94 point something. So you know it's not going to be 94.9. So they're just right there. So they may already have corrected, you know, they're pretty darn close. So anyway, the difference is 19.1 times $1.46. So their charge is not quite $28. You know, not much of a penalty on the lagging. On the leading, you got to pay for all of it. They don't give you any, you know, give you any amount. So that's just 280 times $1.14. Ah, wait, I'm just getting wore out on phone calls today. And so that penalty is about what, 320 bucks. Okay, facility charge. Oh Lord, I could have blown this one too. Okay, so this one's a little easier. It's your contract demand times 93 cents, I believe. And they got a sliding. If it goes above 10,000, then they've got a sliding scale. You have to break it up in pieces, but this one didn't. So we got about, and that's because they're taking their power at fairly low voltage. They're not taking that 161 kVA, you know, or kilovolts. I don't blame them. I wouldn't want any of that stuff around. Okay, and so yeah, if you add all that up and then take 1.5%, you get about $4,000. So my now corrected answer is 270,644, something like that. Okay, are we good? All right, well, let's see if y'all can correct my second one for me here. This is more just on the capacitors and power factor and triangle and all. Okay, so let's see, basically, these are just the answers. I've got to, I'm just kind of looking at the bill as given, real demand. And this is pretty big operation. This is Wapaka in Etowah. So on peak demand, 15,005 or 854. Off peak demand, 16,115. So those are the two real demands. The max demand, just the bigger of those. Pretty easy. Power factor for this one, it'd be, but it's the real, and then, let's see, I guess I calculated it. Let's see, here's the kVA. What is that? Q5. I don't know what I did now, divided by R11. Oh, well, that's just dividing by the, that's calculated. That's one way to do it. But anyway, I think that power factor is actually given to you. Is that right? Have I got this thing? Let me see here. I may have this thing all crazy. On peak power factor 9. Yeah, 98.7. No, that's correct. Okay. Well, that was on the bill, so I didn't calculate. I didn't say you had to calculate it. If it was there, you could just put it down. So I put it down. And then if you know the power factor, then you can divide by power factor to get apparent power. Okay. So that's okay. And yeah, I was looking at load factor. That's where I was going nuts. Okay. And then this is off the bill. It's the same arithmetic here. Okay. Peak kVAR for on peak, that's just doing Pythagoras' theorem on the power triangle. So that's the on peak, that's the 674.5 squared minus, let's see, on peak, the 15,854 squared square root. So that gets you that. Do the same thing for the off peak. So 7895.9, just repeating power factor. you got to take the arc cosine. So I got 26 degrees. I actually did that. Oh, there we go. Okay, and there's that one. Let's see, allowable K-bar. So that's my peak demand times 0.33 is, I guess, kind of redundant. The metered, the difference. So that's the penalty K-bar. That's what I have to pay for. That's the cost times $1.46. Let's see, cost of bleeding, that was $6.17. That's times $1.14. So there you go. K-bars and capacitors needed. So that's will get us out a penalty. That'll get us up to the 95%. So I swear I've got umpteen different versions of this solution. Anyway, I've got monthly savings of about 4,500, about 206,000 in cost. Annual savings, I need to widen my field. About 52.6, payback 3.85 years. I swear I had different numbers earlier, but I don't know. Y'all agree pretty much? Okay, so it should be something along those lines. I mean, it doesn't have to be perfect, but I mean, you know, the idea, I just want you to kind of understand these concepts and know how this stuff gets done. Okay, I think I've butchered that one enough. Let's move on. Let's see here. Okay, so do you appreciate that nice homework, thermo homework I sent you? A little bit larger than the average problem. I'm sorry. I usually start off with some little ones, but I just thought, you guys don't need the little ones. It's time to step up to the big ones. So anyway, this is the last example problem in that file, that scanned PDF that I sent you. I mean, it's similar in nature. I thought we might talk through this a little bit. I'm probably not going to go through every little calculation here, but anyway, like I said, you have a copy of this. It gives all of the details here of the states and all that. And we'll jump back and forth this a little bit, but anyway, let's look at the, let's just look at the cycle first.
When will that homework be due?
A week, say a week from today, you know, give or take a little. It's not too bad. The first one looks big, but I sent you all the state points. So if you have the state points, then all the other calculations are pretty trivial. So the first one, while it looks nasty, really isn't. The second one really is nasty because you have to go find all the state points. So the second one will take you a bunch of time. The first one shouldn't take all that much time at all. It's just kind of making sure you know how to do the balances on the feed water heater and that sort of thing. So there you go. So we've got a main steam flow coming out at 1 here. We've got 2 extractions. We've got a closed heater and an open heater. So after we finish with the first turbine, we go back, we do the reheat, and then we come back at 440, go into the second turbine, do a partial expansion to 5. We have our second extraction, Y double prime. The terminal Y prime is the fraction of the main steam comes out in the first one, and Y double prime in the second one. So then we make our way all the way to the end of the turbine. So we got 1 minus Y prime minus Y double prime coming into the condenser. We're rejecting heat probably to a lake or a river. Could be the atmosphere. They like to put these things on bodies of water so that the heat transfers better. And then we've got our low pressure pump pumping out of the condenser up to the open heater. And of course, we got the Y double prime extraction coming in. They mix together And this puts all the flow back together because I got 1 minus y prime minus y double prime coming in at 8. And I got y double prime coming in from the extraction. And I got y prime being trapped back from the closed feed water heater. So this puts all the flow back together again. So I have full flow through pump number 2, through the closed heater and back into the boiler. You know, closed heaters just got extraction here. These don't mix. So, and these pressures in the heaters are the extraction pressures. So extraction pressure at 2 would be 2 megapascals, and at 5 would be 0.3 megapascals. You know, so I don't know. Not going to spend too much time on this. But there's your TS diagram, which, you know, sometimes if you get asked to the TS, just drawing the TS diagram, may be one of the harder parts of the problem, just to, you know, looking at the picture, getting all that laid out correct. But these are isentropic turbines. You can see that, isentropic pumps. We're not generating any entropy. Your second problem, you have, I think, 85% for your isentropic efficiency on everything. So you'll have to bend those over. So you got an extra stage, extra step on that, which adds some complication. But, you know, gosh, where are we? I guess 11, expect, let's see, is 11 probably to stayed in the boiler? Yeah, we're going in the boiler at 11. So main steam, you know, feed water at 11 to 1, partial expansion to 2, that'd be an extraction point. Then we come on down to 3, then we go back to reheat. And we've got our pressures on here, 8 megapascals down to 2, down to 0.7. Reheat to 440, we're 480 on the main steam. And then we expand, that's the second extraction, and then on down inside the dome. Condense from 7, first pump to 8. And let's see, is 9, what's 9 coming out of the heater? Yeah, 9's coming out of the open heater. And they show it as saturated. That's pretty common, nice assumption. Probably not really, but pretty close. And then second pump, and then the second feed water heater. So you see the feed water heaters do a lot of the temperature increase in the liquid before it actually gets back in the boiler. And that's the purpose, to increase that average temperature during the heat addition. So, I don't know. We can look at some of this. The bunch of assumptions on the trap. The trap is your friend. When you see the trap, that's throttling, and HN is equal to H out. So if you're ignoring kinetic potential energy, which we always do, so, you know, when you see that, you can automatically, when you find H12, guess what? You got H13. So, oh Lord. Man, I'm a popular guy today. Must be all the bill collectors chasing me. Okay. Let's see. I'm not going to read all this to you. I did, when I scanned it, I screwed up. So there's actually 6 assumptions. So you got to jump a page, and then you go back up to the next page. I should have rescanned it, but I didn't do it. So as you go through this thing, it's going to go find all these enthalpies, song and verse. And so I'm not going to do that. I mean, you guys, I think, probably are okay. When you work these things, I don't care if you use like a properties calculator. You can download something, you can find them out there. That's fine. I just, you know, if you don't know how to find these properties, then come to me and let's go spend 30 minutes playing on the board someplace and get you back up to steam, because you don't want to graduate not being pretty confident with the steam tables. And if you take the FE exam, they will, which I encourage heavily, they will pound you pretty good on steam tables. So, Okay, notice here's the pump trick, you know, H8 is H7 plus VDP. And if you had an isentropic efficiency, you would have to divide, because this is the isentropic work, VDP, so you would just divide by the efficiency to get that enthalpy at 8. And notice, if you just put in KPA, you're good to go. You put in megapascals, you got to put in a factor of 1,000, make your units come out. So he's playing the pump trick on both of the pumps. And then you just go to the high pressure heater and do the energy balance. So you can see, we'll talk through that equation. Let's go up to the picture. So high pressure heater right here, summation of mass times enthalpy in is equal summation of mass times enthalpy out. So what have I got? I got an H2 coming in here times Y prime. I've got an H12 times Y prime because this is just condensing. So this flow coming in as steam is equal to the flow coming out as condensate because we got steady state operation. So on the coming in side, I guess I've got H2 times Y prime. I'm coming in over here at H10 and the mass flow rate is 1. So I don't have any multiplier on that. And then coming out, I got H11 and coming out, I got H12 times Y prime. Set those things equal, factor out your Y prime, and bingo, you got the equation. Once you got all the enthalpies, you just plug that puppy in and there you go. So we got about 15.22% coming out at Y prime. And once you have that, then you can go, because see, Y prime appears in the energy balance for the second feed water heater. So that's why you don't want to do the low pressure heater first. Okay.
Dr. Cunningham?
Yes.
So in the homework, it asked for the fraction of steam diverted by to the heat exchanger. You said that all the steam that goes in comes out as condensate.
That's correct. From a closed heater. Yeah, here, let's go back up to the picture.
Yeah.
Say right here, here's your closed heater. So say, I mean, this is just a heat exchanger. There's no mixing of the mass flows. Okay. So, this is all inside tubes, all this feed water, and this steam condenses on the outside of the tubes and then falls down as condensate in the bottom and then is trapped. This is all saturated liquid, is trapped back to this open heater to put that liquid back into the flow.
Okay, so we're solving for how much is going to leave the turbine. That's what we're trying to find.
You're solving for this Y prime.
Okay.
Yeah, I understand. The language is a little bit different.
Yeah, I was just confused on the what we were solving for.
You just want the extraction fractions or percents. So
Alrighty.
every time you got one of these, you want to know what fraction it is of this main steam flow.
Okay, that makes sense.
Like we're doing here. That's why we're talking through this. Good question. Anybody else out there got questions? Fire them out. Don't be bashful. We can't even see you. Okay. Now, if I can figure out where the pages are. Okay. Oh, that's right. We were going to do the second heater. I'm sorry. I'm going to go right back up where I was. So we'll just talk through the balance on the second heater. Okay. So, summation of mass times enthalpy in equals summation of mass times enthalpy out. So coming in, we got three ins. We got an in, and an in, and we got one out. Okay. So coming in, we got y double prime times H5. And we've got 1 minus y prime minus y double prime times H8. And we've got y prime, because this is y prime over here, so it's y prime out of the bottom, gets trapped back. So this is y prime times H13. So all those added up have to equal to H9 times 1, because that's the mass flow qualifier. So it's all put back together exiting the open heater. And so if you do that math and do just a little bit of algebra on it, then you will be right back down here to this equation right here. So he just wrote it all in once. He say he's got a negative H9. So that was over here and he brought it over. So that's the rest of it. So you just got to factor out. And of course, now you know you have a numerical value for y prime. So you just insert it, and then you can solve by factoring for y double prime, which comes out 9.41%. Okay? It's not really too bad. You just got to get, a few of the fundamentals firmly in your mind. Once you got all that, I didn't even have to work it. I had a solution and no problem to it. Instructors are so lazy. I swear. But anyway, I think you can find all that. That's finding all the state points. Let me see. I even sent you this, didn't I? Yes, I did. Let's see. Let's look at the. Okay, so back up here. So those are all the states. Oh, 833. I don't know that that's the right. I don't think this is this the solution? That's not the solution to that problem. It's up on this page up here. It's going to say they're not using the y primes. We got a problem there. Okay, so this is where we go. Okay, so for the turbine, and this is per unit of steam, of main steam flow, m.1. So it's just the enthalpy difference, because from, and this is the first turbine, right? And so the first turbine has 2 sections. So the first section is the full steam flow, so there's no qualifier. So it's just H1 minus H2. But then we extract y prime. And so for the second part of the first turbine, it's H2 minus H3, but we have to multiply by 1 minus Y1 because all of the steam doesn't go through the second stage. Okay. And so then this is just plugging in our enthalpies, and it was 15 point something. So that's 1 minus 0.15, was it 22, I think. And so that first turbine is going to produce 572.9 kilojoules per kilogram. We can go up and look at the picture just to make sure that we're not. So that first part, H1 minus H2 is the full steam flow. The first extraction comes out 15.22%. And then from H2 to H3, we've got 1 minus Y1 times that enthalpy difference. And that will then be the total work out of this first turbine. And then, so let's go on back down. Okay, and similarly for the second turbine, so the mass flow coming into the second turbine is 1 minus Y prime, because it's long gone. And so then that enthalpy difference is H4 minus H5. And then we have the second extraction, Y double prime. So then that mass is out of there. And so for the last portion of the second turbine, the enthalpy difference is H5 minus H6, but the flow qualifier or multiplier is 1 minus y prime minus y double prime. So we got all the numbers, we plug them in, and we see that low pressure turbine is producing 720.7 kilojoules per kilogram. Okay. And then for the first pump, it's only pumping 1 minus y prime minus y double prime. So that multiplier goes times the enthalpy difference. So the 1 minus y prime minus y double prime numerically is 0.7537 times that enthalpy difference. So we get 0.22 kilojoules per kilogram for the first pump work. That's the condenser pump. The second pump pumps everything. So you got the full enthalpy difference. So that's, and it's going up to the really high pressure, going up to 8 megapascals. And so we've got 8.26 kilojoules per kilogram. Okay. We go back and look, just probably get it pretty much in our head by now. Then we're going to go to the boiler. So for the heat input, we've got two different sections. We've got our main steam and we got our reheat steam up here. So the main steam, it's the full flow. So the qualifier is 1. So it's just H1 minus H11. And for the reheat, it's going to be 1 minus Y prime times H4 minus H3. You got to add those together to get the full boiler heat input, which is right here. So numerically, that's 2984.4 kilojoules per kilogram. So then we pretty well got it. So the cycle efficiency is the work from the first turbine per unit mass, the main steam, plus the work from the second turbine per unit mass of main steam. Everything is per m.1. And then minus the first pump work minus the second pump work divided by the boiler heat input. So numerically, this comes out 43.1%. And so we're given the amount of power in the problem statement. We didn't read, I don't want to read all of that. You all have it. But net power is 100 megawatts. Okay. So if you want to calculate, if you're asked to calculate the mass steam flow, you have to have some absolute number for the cycle. Okay. And so that's what this 100 megawatts is there for. So we come down here and there you go. So this 12.85, that's the net power per kilogram. Okay, that's kilojoules per kilogram on units. So that's what you get on this, all the math in the denominator down here. You know, when you add this and this and subtract this and this, you get 1285.1. And so that's the amount of net power per kilogram. And then the amount of power coming out of the cycle, the full power is 100 megawatts. And then we've got to do some unit conversions in order to make the units cancel. So this is absolute out minus, you know, power generated per kilogram. And so you can solve for the mass flow rate out of that. So it's 2.8, what is that? 280,000 times 10 to the 5th kilograms per hour. So anyway, any other questions? The only thing I think you're asked to do on the homework beyond this is you have isentropic efficiencies. So I give you a little something to think about. Okay, enough of this fun. Let's do some other fun. Rankine cycle. We're almost done with a good old Rankine cycle here, but get to presentation mode, maybe. Okay, so we want to talk about cogeneration systems, and I think we've kind of defined this before, but and this comes out of the thermal book, so I don't know if I'll agree with it completely, but probably pretty much. So cogen means we're going to have two outputs, integrated systems that simultaneously yield two valuable products. And it doesn't have to be electricity and steam, but it basically cogen means that you've got one energy input and you're going to get at least two or more. You can have trigen or quadgen or whatever useful energy streams out of it. So traditionally it's electricity and thermal energy, probably steam. But as we'll see, it doesn't have to be, or it can be much broader than that. Typically provides cost savings relative to producing these separately, because, you know, like we've said, in the Rankine cycle, we can come out of the low pressure turbine with enough pressure and temperature that we can actually do something with all that heat instead of throwing it away. Widely deployed in industrial plants, refineries, food processing. Large industry does a lot of this. I've been in quite a few cogen plants. Gosh, Alcoa had a big one. Oh man, what's the name of it? They just sold it. It's up in the Midwest. They had about a 500 megawatt power plant built in with a big smelter and rolling mill. Man, my memory. Every time I think right at something, half the time I can't think of it. At any rate. It can be based on vapor power plants, which means we have condensing and vaporization, like with the steam. Gas turbine power plants, we're going to talk about next, internal combustion engines, fuel cells. So there's a wide variety of equipment that can be used. Okay, so here's a real simple application, such as called district heating. You see a lot of this in Europe. I know I saw a little town in Russia. We had a 2-week trip, I don't know, it was probably 10 years ago, to Russia when that was Alcoa work. They had bought a couple of aluminum rolling mills, and one was a small town called Belaya Kalitva. We flew into Rostov, got off the plane, walked down on the tarmac, and they had all these soldiers standing around with the equivalent of AK-47s. As the Chechen rebels were known to come across and attack airplanes at that airport. That kind of got our attention. But anyway, that little town got a lot of its space heating from the aluminum plant that had a big boiler. And they would bring hot condensate back, and they would then circulate the heat through a heat exchanger. They would heat some water, and they would pump that water all around town. And the residents would take that hot water, and that's what would heat their homes. So that was a perfect example of district heating. So here, you know, we're making steam, we put it in a turbine, we get some electricity, we come out, they're showing us condensing that steam in a heat exchanger. And in this case, they're showing us producing more steam. It could be more steam, it could be hot water, whatever, that then circulates out to some facility that wants to get heated. And so, you know, that energy gets used effectively. And so there's really not much waste. You know, you've got your boiler loss, you've probably got 10, 12% in stack loss, and you've got your heat transfer losses, and that's it. So that system is going to be probably 75, 80% efficient, instead of a typical power plant that's going to be 30 or 40% efficient and throwing away all of that heat in the condenser. So that's pretty cool. Steam exported to community, electricity provided. Exporting useful steam to the community limits the, yeah, so I mean, when you do that, you don't get as much electricity because you're coming out of the turbine at higher pressure, but you're saving a whole bunch of fuel it would take to heat the town. So Let's see, for instance, to produce saturated vapor at 100 degrees C, 1 atmosphere for export to the community, circulating water through the power plant will condense at a higher temperature and this higher pressure. Yeah. So that's the point they're making. It's going to cost you. You won't get as much electricity, but we get a whole much better thermal efficiency. So lots of words. Okay, so this was actually a diagram that was given to me in China. Okay, so guys, this was probably, I don't know, 8, 9, 10 years ago. I had 2 weeks in China for the State Department and DOE, working at a Lawrence Berkeley National Lab, was the one that set us up. And so I was over there, did some training, and spent a week in Ningbo, which is a large, you fly to Shanghai. Or you know where Ningbo is? Have you ever been to Ningbo? Man, it's a huge industrial. They have an industrial park there. They probably have 50 large manufacturing companies. It's a huge manufacturing park. It's incredible. Well, this was conceptual. I don't think all of this, I mean, I think they planned to build this, but this was conceptual for the Ningbo Industrial Center. And then the next week was at Xi'an. Got to see the terracotta warriors and all that. Xi'an was pretty cool. Oh, the whole thing was pretty cool. But at any rate, so they have this large industrial development. I mean, they have all kinds of different companies. And so some of them are chemical processors. And they had this waste product, this waste gas, that had a bunch of energy in it. They called it heat gas. And so, you know, this is like at 1 MPa, and this is the flow. That's normal meters cubed per hour. So what is that? 4525. I used to know what that was in terms of good old US units, but, you know, I can't remember now. You know, like if you travel something like this, you get out in the world and Lord knows what units they're going to use. They have units you've never heard of. So you got to get on Google and say, what in the world? There was one like tons of coal equivalent was a unit I ran into over there that I had never heard before. But I mean, you know, so you just get the conversion factor and convert it back into something you're comfortable with. And then at the end, you convert it back into something they want to see. And, you know, as long as you don't do something stupid, you're okay. So anyway, this is supposed to be a gas turbine. Now, they provided me with this diagram. I didn't go cut and paste all that. That's not really a very big gas turbine, but nonetheless, you know, it's just symbolic. And so they want to burn a bunch of this heat gas in a gas turbine and make some electricity. Well, that's pretty smart because right now they're just flaring it. It's just going up a stack and they got this big, you know, they're burning it because they don't want to put it directly to the atmosphere. So they burn it and turn it into CO2 and other stuff and then put it to the atmosphere, you know. And I mean, we do that. You know, at least in the old days, they used to flare gas that they couldn't sell out of the oil fields. You'd see the big flares coming up. So stuff still gets flared around sometimes. So anyway, but in order to, you know, we got to run it through a compressor. Part of the gas turbine unit is a compressor. So we're going to up it, they're saying, to 2 megapascals. We're going to put all this heat gas in. We're going to put in some 15 degrees C air. And we're going to burn it. Well, that's good. And we're going to get 11.037 megawatts. 11 megawatts, well, that's like probably twice the power of Tennessee Tech. Well, you know, it's not bad from something you've thrown away. But they're not done. You say, well, okay, but coming out of the gas turbine, we've got all these hot gases that are 488 degrees C out of this turbine. Well, shoot, we're not going to throw that away. So they also have in this industrial park hot oil loops that get used for industrial processes. So I say, well, we're going to take this hot gas and we're going to heat some oil with it. So we've got oil returning at 295 degrees C, and it's coming out at 330 degrees C. That's going out to feed their circulating loop that goes to different users that need hot oil to drive their processes. And apparently, again, I didn't size this, but apparently we need to burn a little more heat gas in this guy. So we're going to put 196 normal meters cubed per hour in, and we're going to combust that too in order to make this unit, this oil unit, work properly. But gosh, it's got some pretty hot exhaust gases as well. They're coming out at 330 degrees C. Well, you know, we need some saturated steam. Well, shoot, that's plenty hot enough to generate some saturated steam at 0.6 megapascals. So that's 7.7 tons an hour. And a ton is, that's a metric. So that's what, 2204 multiply 7.7 times 2204. And that's the pounds an hour of steam they're getting. 7.7 times 2204. Well, that's almost 17,000 pounds an hour of saturated steam. Well, shoot, somebody can use that. We might as well. And so here our boiler feed water's coming in, liquid at 105. And Lori, hey, you might know what this says. What does this say? Can you read that? Cool. Oh, you know, I've never had anybody that could tell me what that said. That's wonderful. Thank you. Okay, so, you know, 105 degrees C boiler feed water in, and saturated steam at 0.6 MPa. I don't know what temperature that is. We could just look up the saturation tables. Almost 17,000 pounds an hour, 7.7 tons an hour. But guess what? We're not done yet. We've got 175 degree exhaust here. And you know what? This is an absorption chiller. This is a chiller that runs on heat that provides chilled water for air conditioning or process cooling. Well, dadgum, why don't we see if we can run this chiller with this exhaust gas? So now we got a hot water boiler. Now we're not making steam anymore, we're making hot water. So what do we got? We're coming back in at 90 degrees C, and we're coming out at 150 degrees C. And I guess that's 36 tons an hour of flow. Yeah. And now we got our exhaust gases down to 115 degrees C. And I guess we just couldn't think of anything else to do with them. So we're going to throw those away. And over here on the chiller, we've got 300 tons per hour of chilled water. It's coming back at 12 degrees C, going out at 7 degrees C. Let's see. I'm not sure. This is the lithium. But I don't know what the air compressor. I'm not sure what that is. I never really noticed that. The lithium bromide is part of the chiller. And this is condensing. Yeah, this is condenser water that goes to a cooling tower. So.
Hey, Dr. Cunningham.
Yeah, louder. Speak up.
I was going to ask how the plants in China and Russia compare to the ones in America.
You know, it just depends. Some of them look pretty darn good, and some of them don't look so good. It's kind of like some of the plants in America. Yeah. You know, you go in I've been in plants within 100 miles of Cookeville that were built in like 1927. You know, old brick buildings that the roofs were leaking in places and this, that, and the other. And then I've been in some that are just almost brand spanking new. And it's the same way in China. They've done, they have a lot of really nice stuff.
Yeah.
That's new because there's been a lot of development in the last 10 or 15 years. You know, so all that stuff, state of the art, brand new. But then the second week we went to Xi'an. I forget what the plant made right now, but that plant had been there a while. And it was interesting. They had some things that were really, really good. The things that we tell people to do over here and they don't usually do. But then there were other things that were really not very good, you know? So it was just kind of like the guy running the plant was pretty smart, but some things he knew about and he had been very aggressive, and some of the things he didn't seem to understand completely. And so it wasn't so great. It was like his, the deaerator on his boiler, they have to vent some steam because that drives off the air and the non-condensable gases. That's out of the open feed water heater. He didn't understand a deaerator. He thought that was a steam leak, and he closed it off.
Oh,
And when we got it, we were walking around outside and we saw all these valves and stuff that were discarded. And we asked him why, and he says because they had pitting, corrosion, oxygen pitting. Well, probably they had oxygen pitting because he wasn't venting any air from his deaerator because he didn't really understand. And so it was causing him all kinds of corrosion issues. But then we went inside and he had a bunch of VFDs like on his boiler feed pump and his combustion air fan, which is stuff we tell people to do all the time over here that half the time they don't do. And so on one hand, he was really, really good. On the other hand, we got some improvement we can do over here. So
yeah. Sounds like you've had a pretty cool career.
yeah, I've been very blessed. I've gotten to travel a little bit. Okay, but anyway, I just think this is awesome. I mean, anytime I get into my cogeneration discussion, I want to pull this up because man, so we got one input up there, heat gas, and how many outputs do we have? We've got an output here of power. We've got an output here of hot oil. We got an output here of steam, and we got an output here of hot water that eventually turns into chill water. So what do we got? Four valuable outputs. So this is like quad generation. 1, 2, 3, and 4. Yeah. Out of a waste product. Something that they were throwing away. Now, wow, that's pretty darn good. I was pretty impressed when I saw this. So anyway, I had to write this up as part of my report. And so I was too lazy to make my own diagram because I had their diagram and it was going to China and already had Chinese written on it. I didn't know what it said, but I figured it was probably appropriate. So I just used it. Anyway, all right. Extra G, we ain't doing extra G in here. We're done with this one. Okay, so how are we doing here time-wise? We got a few minutes. So our next topic to tackle is the Brayton cycle. So we want to talk about, and I'm going to run through the basic thermo slides pretty quick, and then I've got some stuff from TVA, their combined cycle plant that I haven't dusted off yet, but it'll take us, I don't know, a couple of classes to get through this. But because what happens is we're going to mate a Brayton cycle gas power cycle with a Rankine cycle, and they call it a combined cycle. And those are the plants that are still getting built, unless the current new administration kills them because they do use natural gas. So not sure where all this is going to go right now. All this this politics, man, it can make a big difference in the direction of things. Because, yeah, I mean, we were at Magnolia TVA plant. They're about 60 miles south of Memphis. They've got 300 megawatt combined cycle units. So what, in the summer, they pay $280 a million. This was year 4 last. They're paying $280. They're right on the pipeline. They're paying $280 during the summer, $320 per million BTUs. In the winter, average of $3 a million BTUs. Man, you'll burn that all day long to make electricity compared to burning coal. Because coal, you know, coal's dirty and it's got a lot to clean up, and you got twice the CO2 emissions, and you got mercury, you got sulfur, and you know, if it's anywhere close, I mean, the coal price for TVA is probably $225, maybe $230, maybe $240, depends on where they are and what they're buying. Well, you know, 230, 240, and $3, not that far apart. And you've got ash disposal you don't have to do, and you've got a lot of other costs. So when you calculate all the cost, $3 gas is probably cheaper to burn than 230, 225 coal. And you don't have very many of the environmentalists haranguing you day and night, calling you, yeah, take that coal plant offline, So anyway, but now if we stop fracking and you see this, I don't know what's going to happen as far as the grid is concerned. If we stop fracking, the gas price doubles or triples. What are these utilities going to do? They can't afford, or you might not want to afford the electricity that they generate at 3 times the gas price. So, and then economically, what's that do to the industry? I mean, it's complicated. So anyway, all right, well, that's enough fun stuff. Let's do the gas turbine cycle. So, these things, they go up quick. They don't cost as much as the nuke or the coal plant, that sort of thing. Gas turbines are really good, stationary power generation as well as powering vehicles. Aircraft propulsion. Gas turbines are increasingly used for large-scale power generation. And they're primarily fueled with natural gas. Yep. So there's a distinction. There's what they call the open cycle and the closed cycle. I think all the real ones operate on the open cycle, but for easy analysis and making things easier on students, the guys that write the textbooks like to do some of the closed cycle stuff because you avoid combustion. If you do the real analysis on the open cycle, you have to consider the combustion. And combustion is complicated and messy, okay? So the open is what you're gonna see out there in the real world. What happens over here on the open side is we pull in air, we compress it, we put it into a combustion chamber with fuel, natural gas, we burn it. So coming out, we have not only high pressure, but we have hot with high pressure, maximum energy to put into the turbine. So that, the hotter and the higher the pressure, the more potential we've got to generate power and the more net work. And we power the compressor off of the same shaft as the turbine. So what comes out on this side is what's left over after the compressor operates of what the turbine can generate. And then basically we throw the products of combustion away. We may do some heat recovery or something like that, but basically we wind up throwing those gases away eventually. Now on the closed cycle, basically instead of considering the combustion, what we say is, well, we'll do that combustion someplace else. We'll worry about that another day, and we'll show this energy input instead of the combustor. We'll just show that as a heat exchanger, and we'll just have some nice Q dot in that we're putting in. And likewise, to close the cycle, we have to assume that these products eventually come to the same temperature as the air. And if you dump them into the air, they will come pretty quickly to the same temperature as the air because they're not going to heat up the atmosphere. Not right there around the plant. It won't happen. So you could either make that assumption that they're just going to mix together and come to the same initial air temperature, or you can say, well, we're going to envision this heat rejection to close our cycle and get back over here to state one. And we're going to do control volumes and mass and energy and entropy balances around everything. So kind of the standard deal, open and close. So there's the open mode gas turbine is an internal, it's called internal combustion because the combustion happens inside this component, the combustion chamber. So air is continuously drawn into the compressor, which compressed to a high pressure, and you get a nice temperature increase at the exit of the compressor as well. So we got our nice little blue ball going up to the compressor. Air then enters combustion chamber. It mixes with fuel, and we burn the gas. That's pretty slick. We got the fuel and the air mixing, and then burning. Okay. Combustion product exit, elevated temperature and pressure. Bless you. And then they go through the turbine where the gas expands, does work on the blades, and is discharged. So, and then part of the turbine work is used to drive the compressor, and the remainder available as network output to drive the electric generator or do something else with. But as far as we're concerned in here, it's probably to make electricity. Okay, so here's the closed gas turbine cycle, operates as follows. Gas circulates through 4 components. It's the same air, typically, is what we would assume. Turbine, compressor, 2 heat exchangers at higher and lower operating temperatures respectively. So basically, we got the same air. It just keeps going around in a circle. Through all 4 of those components. Turbine and compressor play the same roles. Nothing changed for them as the open gas turbine. As gas passes through the high temperature heat exchanger, it receives energy by heat transfer from an external source. So we've got some kind of external combustion or something going on, providing the heat that we put in through the heat exchanger. So that's the terminology, external versus internal source. And then we complete the cycle by heat transfer to the surroundings as we go through the low temperature heat exchanger. So, gas turbines are they're not bad. Okay, so heat transfer associated with the higher temperature heat exchanger is of the closed gas turbine originates from external source, which may include, you can burn anything. You just got to have heat. You got to get heat someplace that you can transfer in. So it could be all kinds of stuff. Fossil fuels. Waste heat. You could have waste heat from, even though the waste heat system that I've here discussed, I don't see many of them, is the organic Rankine cycle, which is the basic Rankine cycle with the refrigerants or the organic working fluids that boil at such lower temperatures. So, because not that many industrial applications have high enough temperature waste heat to really generate a lot of steam. There's a few, but most not so much. Solar thermal energy could be a source. Gas-cooled nuclear reactor could provide this. Okay. Okay, so then, to start off, make it as easy as possible, we do what we call this air standard, which is more simplifying assumptions to make the analysis simpler. Okay, so the air standard analysis assumptions are working fluid is air, which behaves as an ideal gas. So you get all the ideal gas relations. Temperature rise that would be brought about by combustion is from heat transfer from an external source. So we get rid of the combustion. The air standard analysis avoid complexity of combustion. We've already said that. And even the cold, so this is the terminology, cold air standard analysis even assumes specific heats are constant at their ambient temperature values. So how many of these assumptions you invoke, the more the cold air standard analysis is probably the simplest you can do, but the answers are not going to be terribly realistic. And so the more you start relaxing this stuff, the better the analysis, but the more complicated it becomes. So, okay, let's see. Schematic of a simple open air standard gas turbine power plant is shown. Energy transfers, heat and work are positive in the directions we show them. So we got air circulating through the components. This is it's a little bit redundant. Air into the compressor. Compress from 1 to 2. And then we're going to put it into the heat exchanger. 2 to 3 is going to be a temperature rise. Really it's by combustion, but anyway, we're going to do it with Q dot for the heat transfer. High pressure, high temperature expands through the turbine. So these are a little bit redundant, I guess. And then air returns to the surroundings of state 4 with the temperature typically much greater than state 1. And then guess what? We're going to say that basically the air mixes and comes back to the same temperature as 1, which is required to complete the cycle. So, there we go. Process 3 to 4, that's the turbine. And of course, that's going to generate power. That's going to drive the compressor and the generator. Air typically returns to the surroundings at state 4 at a temperature much greater than 1. And so, so this is for the, if we're going to close this with a heat exchanger, then we just imagine that this heat exchanger is there in order to get us from 4 back to 1. Okay, so this is what we mean by the Brayton cycle, the air standard Brayton cycle, 1, 2, 3, 4, 1. The compressor pressure ratio, P2 over P1, is a key parameter, operating parameter for the Brayton cycle. So we'll talk about increasing, decreasing pressure ratios as we go forward. Analyzing each component as a control volume, steady state, assuming that the turbine and compressor are adiabatic, ignoring kinetic, all of our standard simplifying assumptions, then we're going to get the following equations. Well, guess what? The turbine work is the enthalpy difference across it per unit mass through it. The compressor work is the enthalpy difference across it. The heat addition is the enthalpy difference across it. And the heat rejection is the enthalpy difference across it. So, it shouldn't be too hard to come up with the equations. And I tell you what, I think I've droned on about enough on this. This is a good place to stop. So we'll cut it off here. I'll be sending you some more files, and you be working on your homework, and I'll be working on your next homework, trying to get it ready for you. So I hope everybody has a great weekend. Have any questions or anything, email me or give me a holler, and do my best to help. So see you guys next week. Take care.